Thank you and for attending this webinar. And the title of this webinar is Spectral Accuracy, Elucidation of Multiple Ion Fragments. And let me introduce myself. My name is Don Keel. I'm the Vice President of Marketing and Product Development at Cerno Bioscience. I have a PhD from Ohio University in analytical chemistry. And I'd also like to thank my coworker, Yongdong Wang, for assistance in this presentation. Yongdong is the CEO and President of Cerno Bioscience, and he's another analytical chemist with a PhD from University of Washington with a specialty in chemometrics. I'm just going to spend a brief moment here to talk about give you a little background on our company. Cerno Bioscience was founded in 2003, so we've actually been around for quite some time now. Our headquarters are located in Norwalk, Connecticut, in the United States, and we specialize in mass spec calibration and analysis technology. The company has over 14 granted and pending patents worldwide covering this unique technology. And we actually make our applications and calibration technology available through a product which is called MassWorks. And MassWorks is a standalone post-acquisition application software. Was introduced at PitCon in 2006, version 1, where it received the recognition with the bronze medal. And we're now at version 4, and we're soon to be released a version 5. The software, as I mentioned, is a standalone software platform which directly reads data from most commercial mass spec systems. And since 2006, since introduction, we've delivered we have thousands of customers worldwide across the U.S., Canada, Europe, Japan, China, etc. And again, the key function of this software is accurate mass spec calibration and analysis for mass formula determination, compound ID, isotope analysis, and mixture analysis. This is a brief outline of what we're going to try to cover today. First and foremost, we're going to talk about the importance of mass spec peak shape calibration and the concept of spectral accuracy. Next, we're going to cover how spectral accuracy can be utilized for the elucidation of EI fragments, whether they are mass spectrally overlapped or not. We'll talk a little bit about the value of this unique approach for educational and undergraduate research and teaching. But most importantly, we're going to talk about the implications of this innovative approach to other real-world applications. And we're going to look at a few real-world examples, including deamination and deamination of other biologics modifications, hydrogen deuterium exchange mass spec experiments, and metabolic flux studies. First, we're going to talk about the peak shape calibration and spectral accuracy. We're going to look at the principles of mass spec calibration, and then we're going to look at the Cerno approach, which is a new comprehensive mass spec calibration approach, which provides for about 100 times improvement in centroiding and mass accuracy for unit resolution systems such as single quad, LC and GCMS systems. But perhaps more importantly, it also provides a dramatic improvement in what we call spectral accuracy for both high resolution and unit resolution mass spectrometers. Let's look at a typical mass spectrum as one might visualize it from a commercial mass spectrometer. And what's typically shown is the raw signal from a a mass spectrometer is typically processed by the mass spectrometer data system to provide a view of the data as centroided for the user analysis. And this is just a simple example of data that's been processed and presented to the user as centroided data. However, in reality, the raw signal from a mass spec is actually a continuum, which is commonly known as a profile or raw scan data. And this continuum data is typically processed and presented to the user as the centroided data, which we saw in the previous slide. The centroid data on first looks does look like a theoretically calculated mass spec with intensities at the given mass locations. If you look more carefully, however, what is revealed is that the true mass spec contains much more than just this centroided data. For example, under the A+1 cluster, one actually sees multiple isobars, indicating the presence of carbon-13, nitrogen-15, sulfur-33, so on and so forth. And it provides key elemental composition information that would normally have been lost with the crude centroiding that's done in a lot of mass spectrometers. Under the A+2 cluster, though weaker, it actually contains even more detailed information regarding elemental composition. For example, the presence or absence of sulfur element in the ion. Due to this information being lost in the centroiding process, the determination of elemental composition is only considered feasible when the monoisotopic mass of the ion can be accurately determined to within a few ppm accuracy from a high-res mass spec system, such as the time-of-flight system, Orbitrap, or other high-resolution mass spectrometer. But in fact, if we look at the profile data, and here is just an example of the mass spec profile data actually these are theoretically generated spectra for a number of molecular formulas, all with very similar masses. But because of the difference in the isotope distributions and ratios, you can see that every spectrum for each formula has a very unique fingerprint. And this is very valuable information that we can use to perform accurate formula identification. In the next slide, we're going to talk a little bit about conventional mass spec calibration. What's typically done is the measured monoisotopic peak is corrected for mass position only. So if that's the measured mass spec and the blue is the theoretical mass spec, what we do is we do a correction for the position, for the mass position only. If you look at the two curves, you'll see that the theoretically corrected mass spectrum does not generally overlie the measured mass spectrum very well. And this is because the mass spec curve, the measured mass spec curve, is undefined. It's really the line shape that's in that spectrum is really a function of the errors in a mass spec electromagnetic lens. If you think of a mass spectrometer as a spectrometer, the electromagnets that are directing the ions are really a lens, and it's really not a very good lens. And in fact, if we change the tune of our mass spectrometer, we actually will change the shape of that profile curve. So if we could somehow correct for these errors that are introduced by the instrumentation, in theory, we could match these two curves much more precisely. That is, the theoretically generated mass spec and the measured mass spec. And this ability to match the measured and theoretical isotope pattern is what we termed spectral accuracy. So our ability to measure this to a high degree of accuracy, it would enable us to perform much better analysis, formula ID, mixture analysis, etc. In the Cerno mass spec calibration approach, it's a very different approach. It's a patented approach of calibration that takes full advantage of the theoretical basis of mass spectrometry to create a proper calibration function that not only accurately locates the peak position, but it also suppresses the noise, and most importantly, corrects the peak shapes to a mathematically defined function. This is how it all works. First, a known ion or standard is measured, and that's shown here in the graph. This is the standard from which we're going to derive our calibration. First of all, the software MassWorks examines the standard ion and calculates a mathematically defined line shape that closely approximates the measured line shape. For example, it may be determined that the measured line shape is closely approximated to a Gaussian line shape whose half-width is about 0.32 Daltons in this particular case. This will be used as the defined line shape to calibrate to. Next, we calculate the theoretical mass spectrum for the standard ion. And this can be done very accurately. Because mass spec is one of the few techniques where we can calculate the theoretical spectrum to a very high degree of accuracy, because we know the atomic masses to many decimal places, and of course we know the natural abundance of the isotopes. So again, it's one of the few analytical techniques where we can calculate spectrum very precisely. So the spectrum that I show here is calculated from the known atomic weights of all atoms, including taking into account the addition or subtraction of the electrons, which determine the charge state. In addition, we know please make sure that you mute your microphone. In addition, we know the natural abundance of the isotopes, and from this information, we can accurately calculate the theoretical spectrum. Note that the theoretical spectrum has infinite resolution here, and the contributions of the different isotopes at n+1, n+2, etc. are very apparent. However, our real measurement does not have infinite resolution. A real spectrometer has finite resolution. But we know the approximate resolution from our previous line shape estimation. So what we do is very simple. We convolve the defined peak shape function with our ideal theoretical function. So what we have now is a mathematically ideal theoretical mass spectrum that's based on first principles. Now what we do is we compare the theoretical to the measured spectrum, and from that we can derive a calibration equation. That calibration equation is really a vector function, which is shown here in green, and really explains the difference between the theoretically correct mass spec and the measured mass spec. So that's our correction function. And it will, when applied to any measured ion now, after we've now calibrated our mass spec, it will produce a spectrum which would match our theoretically generated spectrum within the limitations of the noise of the measured data. So when we apply this to our unknown ion, we calibrate the mass spectrum with a known desired peak shape, and that's very important. Now, once we've determined this calibration function, we can apply it to our measured unknown or sample spectrum. We simply apply the calibration function to the measured spectrum to obtain a mass spectrum, and that's, we're now applying this correction function, and you can see that the resultant function is corrected not only for the mass positions, but it's also corrected to a known mathematically defined line shape function. The calibrated spectrum for both mass and spectral line shape is shown in red here, and can be compared to the uncalibrated spectrum, which is shown in blue. So again, note that the calibration corrects for both the line shape and the mass position. Okay, once we perform this calibration, by calibrating the mass spec line shape to a mathematically defined function, This allows us to do very high mass accuracy determination, even on so-called unit mass resolution instruments, such as single quad LC or GC instruments. For example, the specified mass accuracy in a single quad GCMS system may be on the order of about half a Dalton, perhaps a little bit better than that. But once we have performed an accurate calibration of both the line shape and the mass position, we can now estimate the mass accuracy to within typically about 5 millidalton, which is about 100 times better than for the typical specifications on a unit mass resolution instrument. The other important thing is, in addition to improving the mass accuracy, we gain a tremendous improvement in what we call the spectral accuracy. The spectral accuracy, that is our ability to match the exact spectral profile of the spectrum, of the measured spectrum, which has been calibrated to a theoretically generated spectrum. This is a very powerful fingerprinting tool, which enables significant improvements for both high and low resolution mass spectrometry, including it enables our ability to perform much more confident formula identification, because not only can we use the mass position, but we can also use the calibrated line shape to get a unique pattern, isotope pattern, which can be very accurately measured. It also allows us the ability now, even if ions are unresolved, we can, since we know the exact pattern now of these isotopes, we can deconvolve them, so we can actually resolve mixtures, and we're going to look at that in some of our examples at the end here. And what we see here in this plot is the red line is actually the calibrated measured spectrum, and the green line is a theoretically generated spectrum, which is generated using that same line shape that we determined when we did the initial calibration. And you can see that the match is excellent, okay? This is what we call spectral accuracy, our ability to match the entire isotope profile with a very high degree of confidence. So those two things together, mass accuracy and spectral accuracy, are what really enables us to do things with mass spec that previously were very difficult to do without this type of calibration. If you want to know a little bit more detail about how this works, because I'm not really going to go into it today, I would direct you to a feature article that was published in Analytical Chemistry in 2010, September 1st, volume 8217. And that will describe in great detail how this worked and some of the significant advantages of this calibration approach. Okay, let's move on, and we're going to talk about a few application examples. The first one will be what was in the title of this webinar presentation, and we're going to talk about GCMS multiple ion fragment identification using spectral accuracy. And the next example we'll talk a little bit about will be on the quantitation of deamination of oligonucleotide using LC-TOF. And our third example will be the quantitative analysis of deuterated pyrene as analyzed by GCMS. And finally, we'll look at the direct quantitative analysis of unresolved metabolic isotopologs with Q-TOF. Okay, and our first example, this is a GCMS run of OFN. OFN is octafluorolnaphthalene. It's used as a standard in GCMS for evaluating the sensitivity. It's a nice example system that we're going to take a look at because it provides a nice fragmentation pattern by EI. And what we see here is really a number of things going on. This is actually the software. It's a screenshot. And the lower portion down here to the right corner, we can see the fragmentation pattern of the OFN. This is the molecular ion. And then these are the fragments that, of course, have some loss of some molecular loss, some atomic loss, which we can hope to determine here. The first thing we do is to understand is that this has already been calibrated. In fact, in this particular case, this Agilent GCMS data, and when we loaded the run into the software, the user had run the calibrant gas at the end of the run, and automatically located that and automatically generated the calibrated data here. So that's the OFN molecular ion here. What we have in this window here is our search window. Here we can specify the elemental composition that we can set constraints on to perform a molecular ion search. And we also over here set the range in which to search over. So we're just going to search the profile and the mass positions of this molecular ion here with the software. And of course, all the software is doing is it's generating theoretical mass spectra to search against. And because it knows what the line shape was used in the calibration, it can go and generate theoretical spectra to match using that exact same line shape to get a very good match. And the list here that's produced by the software, as you see on the left, shows a list of matches, which are actually sorted, can be sorted either by mass accuracy, this column right here, or by spectral accuracy. As it turns out, in many cases, your spectral accuracy is actually the better way to do the search. And in fact, when we do search this ion, what you'll see is the best result, the best match that comes up is indeed the correct one. And the spectral accuracy match, or the goodness of match between the measured ion and theoretical, is 99.7%. That's an excellent match. In addition, because we also did an accurate mass correction using our calibration approach, the actual error in the mass accuracy is only about something less than 2 millidaltons. Okay, gives you an idea of the power of this calibration approach. So here, without any mass spec library, just using the molecular ion, we can uniquely identify the small molecule using GCMS and the calibrated data using our MassWorks application. In the next slide here, all I've done is I've zoomed in to that molecular ion, and what you see here is the molecular molecular ion peak. This is M+1, M+2, and this is an overlay of the red, which is the theoretical spectrum, the measured spectrum, and the green, which is the theoretically corrected spectrum. And you can see the match, the overlay is very good, it's very tight here. That's the best match, and that has the best spectral accuracy. So that's the one that came out at the top of our match. If we just drop down to the second best match, you can see now that there is a significant deviation between the measured calibrated spectrum and the theoretical spectrum, okay? Enough to uniquely differentiate based upon the isotope pattern alone which of these is the correct match. And again, the top two matches, those two molecular formulas are both within 2 millidaltons of each other. So even with a high resolution mass spectrometer, it might be difficult to determine the correct formula ID based upon the the mass accuracy alone. Okay, the next thing we can do, and this is where it gets interesting, is we can now go in and we can propose what this first fragment might be. Okay, so we have an idea of what the molecular formula is from the search. So what we can do now is we can tell the software is look for the loss of fluorine, okay, and generate the spectral profile, and in addition to matching the molecular line, also measure that first fragment. And if we propose the wrong fragment, of course, the spectral accuracy will not be as good as if we choose the right one. So it's a very powerful technique for basically elucidating the fragments from EI. And so here what we've done is to test our hypothesis. We can tell the software to include the minus F from the molecular ion and to redo the search over a broader range. Notice that we've increased our profile search range from the molecular ion position here to minus 25, which is about the edge. You can see the green overlay there, to about this. So we're going to search the molecular ion and its first fragment, and we're going to assume that the first fragment is minus F, okay? And indeed, what we find out is that the top match again is going to be the correct ion, and we have a spectral accuracy again. We sort it by spectral accuracy, we get a 99.6% spectral accuracy. So that's a very strong confirmation that we have the molecular ion and its first fragment there identified properly. What's also interesting is, in addition to identifying the ion, we can also give you the quantitative information. In other words, what's the relative percentage of the molecular ion to that first fragment? That's easily calculated, and that's shown here in this table, right in the search results. We can continue this process. As you can see here, we've added our proposed different fragments here in the ion series, and the spectral accuracy for the search remains very high, which is a confirmation that we've chosen the right fragments. If we choose the wrong fragments, again, our spectral accuracy will go way down, and it will be indicative of that incorrect assignment. So since the spectral accuracy remains higher, our confidence in the assignments is validated. Note that we can also set a min and max value for the number of ions allowed in the search for loss. So because we actually have multiple losses of fluorine in our mixture results here. We have C10F8, we have C10F7, C10F5, C10F6. So it's actually identifying and fitting all of those molecular, all those ion fragments, in addition to the other ion fragments that we've proposed here. So you can see it's a really powerful tool for really for a number of application areas. One is it's a very powerful tool for structural elucidation, for degradant analysis, and as I mentioned in the beginning, it's also an extremely powerful educational tool, helping one understand MS-EI fragmentation kinetics as it relates to the molecular structure. And it also helps further understanding of fragment patterns from the NIST library. The NIST GCMS library doesn't have assignments for the fragments. It's just searching the overall fragment pattern. We've actually integrated in our latest version of MassWorks. We've integrated NIST searching, and we have the ability to search that library, and you can actually do the search and look at the ion fragments and do assignments from it. So it's a very powerful tool, both from a practical point of view and also from a educational point of view, and just understanding the chemistry of the ionization process. Okay, let's move on to another interesting application of mixture analysis. And again, we can do this mixture analysis not only on ions that are resolved, like we saw in the previous example, but even if they're overlapping, we can still do the fit, because the different ion species each has a unique fingerprint, and we can deconvolve, or we can basically unscramble that mixture by using this approach, because we know exactly what the spectrum should look like, because we've calibrated them to a known line shape, and that's so important. So in addition to searching multiple resolved ions, the same approach can be used to identify and quantify unresolved ion mixtures. So in this example, we can actually quantitatively measure the percent deamination of an oligonucleotide. Okay, so what we have here is we have an oligonucleotide which undergoes deamination. Could be multiple deaminations going on through aging, through stress, and obviously it's a very complex mass spectrum here. But underlying this data is a mixture, and since we know that what the chemical formula is for the loss of deamination, we can actually do the fitting to basically determine quantitatively what the different deamination species are present in this mixture. And what we see here is simply a using other techniques for determining the amount of deamination, and using our spectral fitting, you can see that it correlates very well. So we can directly measure the amount of deamination in the mass spectrum without resolving the mixture. Very powerful tool. This is very difficult to do any other way. If you look over here on the right, I've just blown up a section of the mass spec, and what it's showing there is, again, it's the fitting, it's the overlay of the mixture spectra. So it's a combination, linear combination of the number of different deaminations here with the measured data. And again, we're using that spectral accuracy. By the way, all these papers are published posters or presentations, and I've cited the references here in each slide. All right, moving on to the next example. This is a GCMS example, and what we're doing here is that it's another example of mixture search where we can quite easily quantitate the deuterated species of polycyclic aromatic hydrocarbons. Deuterated PAHs are widely used as analytical standards for monitoring pollutants. And unfortunately, the compounds are very difficult to characterize in terms of the amount of deuteration and what the mixtures are. Again, using exactly that same fitting approach and taking advantage of this accurate calibration and the spectral accuracy, we can quantitatively determine after the reaction has been undergone, this particular user had a rather unique reaction to perform the deuteration of pyrene. But the analysis of the final deuterated species and the quantitation of each one of the species was quite difficult. And this was actually done, I take it back, it wasn't GCMS. I believe this was done by DART ionization. So it's a soft ionization technique. There's no separation involved. And we can accurately determine the concentration of each of the deuterated species. Again, without any kind of separation, which of course is quite difficult here. Okay. In my final example here, we're going to look at the metabolic studies of complex isotopologs with Q-TOF and something we call SCLIPS. The calibration that we use, we have an acronym for using the calibration with the search. We call it CLIPS, which stands for Calibrated Line Shape Isotope profile search. But when you go to high res, and there we require a standard ion to do the calibration. But in high resolution mass spec, where the monoisotopic peak is fully resolved, we can actually use the monoisotopic peak itself as the calibration standards. This means that we don't even require a separate standard calibration in order to properly calibrate the mass spec. So that's a really nice advantage in high resolution mass spectrometry. So here we're using that same calibration approach isotope labeling and quantitative LC-MS profiling together in this application offer a really promising approach for unraveling the dynamics of biosynthesis of specialized metabolites, natural products in plants and other organisms. And the isotope patterns and the ratios and metabolites really harbor really valuable information which traces the biosynthetic history of specific compounds. So this is of real interest in looking at studying the metabolism of these plants and animals, actually. And what's been done here is that these specialized metabolites from tomato plants, actually, were grown. These tomato plants were grown in an atmosphere of CO2, C13OS2. So it's CO2 that has C13 on it, and obviously it's incorporated metabolically in the plant. We can look at the chemistry and metabolics here, and the problem is, of course, is that the C13 is incorporated into these metabolites at a lot of different sites and a lot of different amounts, and to quantitate them, of course, is quite difficult. And again, because there's only one proton difference, so all the peaks tend to overlie on top of each other. But again, by providing our mixture search and by taking advantage of this calibrated spectra, we can actually quantitatively determine all of these species in this for this metabolite as it's metabolized through the plant. That's something that's extremely difficult to do in general, and here we can do it directly on the metabolite by, again, using our calibrated mass spec data. Okay, I'm gonna wrap it up here, and then at the end we'll do questions. If anybody has any questions, again, please send them into the host, and I'll answer them verbally. But in summary, this comprehensive calibration approach of both line shape and mass enables new and very powerful analysis for not only formula identification, but also for isotope and mixture system. And the interesting thing is that it really can be used on any MS system. It can be used on lower resolution single quad systems, all the way up to high resolution ICP or high resolution Orbitrap systems. Provides an advantage really for all of these systems. And again, if you have any questions or would like to contact us about evaluations with your data and your applications using this approach, we'd be happy to discuss that. We work with a lot of different collaborators. We do a lot of publication. If you go to our website at cernobioscience.com and go to the resources section, you'll see a lot of those publications to get some very interesting ideas of what can be done using this calibration approach. And of course, if you're also interested in purchasing the software or just want to have more info, again, please feel free to contact me directly. My email is shown at the bottom of the slide there. It's don.keel@cernobioscience.com. And with that being said, let's open up. If anybody has any questions, please send them in through the chat to the host, and he'll relay them to me, and I'll answer your questions. Thank you.